Okay, I think we'll get started. Today we have a pretty short lecture here, but we want to make a connection between the kinetics that we've been just talking about and the ideas of chemical equilibrium that we were talking about earlier in the course. So a chemical reaction is one that comes to a dynamic equilibrium. So it isn't like the reaction stops at equilibria. The reaction goes just as much as when it's out of equilibria. It's just that the reaction in the forward direction is equal to the reaction in the backwards direction. And so let's see this play itself out in terms of what we've been talking about lately with kinetics. So let's just imagine an elementary reaction. So I'm going to do this all for an elementary reaction, and then I'm just going to say it's true for an overall reaction. We won't work that out in any kind of detail, but we'll just see how it happens for an elementary reaction. So we'll take a very simple elementary reaction. A goes to B, and we have this equilibrium. So we have a rate constant in the forward direction, and then we have a rate constant in the backwards direction. Let's just take an Arrhenius view of this. We have an activation energy, and A will then go to B, but in order to do so, it has to get over an activation barrier of EAF. But B can go to A, right? We can have the backwards reaction, although it would require a larger, in this case, the way I've drawn it, would require a larger activation energy. And so this will settle at an equilibrium where we have more B than A. All right? Now, we can write, since it's elementary, we can write the forward reaction rate as K times the concentration of A and V times the concentration of B. V reverse times the concentration of B. All right, so these are these velocities. Now, let me, and I'm going to change this graph here because I want to make it match with what we've had up here. So let me adjust this graph. So we can dump A and B in the beaker, and we can follow the reaction along the reaction coordinate. And at any given point, we can define our reaction quotient as product over reactant. And then we just let this go to equilibrium, and the long time, or T equals infinity values of the concentration will be K. And that will match this idea that now that I've redrawn it that way, we'll match this idea that we're going to end up with more B than A around. Our equilibrium will lie to the product side. Now, if this was shifted, then we would have a reactant-favored reaction. But nonetheless, we would have this same type of behavior. We would start with reactants, no products, and so our reaction would be going this way. Well, let's look at that from the kinetics point of view. So we start our reaction. We only have reactant, no product. So regardless of what the K's are, the velocity in the forward direction is going to be bigger than the velocity in the reverse direction. So let's just make a sketch here of the velocity in the forward direction. That's going to be fastest when we just started our reaction, so we have the most A around. Then as A reacts to form B, the forward direction velocity is going to drop. But now we're starting to have B around, so the reverse direction reaction is going to start to speed up. So if we look at the velocities of the reaction, the forward direction is slowing down, the backwards direction is speeding up. Now, what happens when they meet? Then we're making just as much forward progress as we are making reverse progress. And this would be the condition of equilibrium. So on the reaction coordinate, right, we would sort of stop here. This would be our long time, because we would just sit here then. If we went any further this way, right, well, then the reverse reaction would be faster, and we'd start to come back this way. And the And likewise, if we went back this way, we would come this way. So we'll settle in on this equilibrium reaction rate. And so at equilibrium, our condition in terms of kinetics is that the velocities are equal. Well, let's set our functions for velocity equal, and then let's solve, let's get the k's on one side and the concentrations on the other. So here are our rate constants. Forward over reverse. Forward over reverse is product over reactant. And so that's our equilibrium constant. So our equilibrium constant is k forward over k reverse. Now, this would be true. I think you can see this pretty quickly that this would be true for any elementary reaction, because these would just be the same. These would just be the conditions here really are just going to depend on the concentrations to whatever is going on, right? And we can write it directly with the stoichiometry. And then the reverse reaction is just the reaction in reverse with its stoichiometry. So they would be raised to their stoichiometric factors if they're elementary reaction. And we would get products raised to their stoichiometric factors over reactants raised to their stoichiometric factors. Harder to see it for an overall reaction. At this level of our course here, Introductory to Physical Chemistry courses, we're just going to accept that this is true even for an overall reaction. And the k's would be replaced with like observed rate constant and observed reverse. So what would we be observing in the beaker? The forward k over the reverse k will give us our equilibrium constant for this overall reaction. All right, so this seems encouraging because it looks like we have brought in the power of thermodynamics, which is a rigorous theory, as we've talked about, into kinetics, which is more of an empirical theory or experimental-based theory, and it lacks the same kind of mathematical rigor, pencil and paper rigor that thermodynamics does. So it looks like we've brought in thermodynamics here. But let's look at this more closely. It turns out we really haven't, because let's consider this reaction, and let's let k forward be 10 to the 5, and k reverse equals 10 to the 3. So these are fast reactions. The rate constant is big. So if the rate constant is big, the reaction's fast. So let's look at this ratio. A lot of k's here, so this is capital K. Would be 10 to the 5 over 10 to the 3, which is going to be 100. So we would have an equilibrium constant of 100, and we would get to equilibrium very fast because our k's are big. But now let's say k was 10 to the minus 5, and k reverse was 10 to the minus 7. Then k is going to be 10 to the minus 5 over 10 to the minus 7. Very slow reactions, but we still get 100. So the fact that we're taking the ratio of the k's loses our time dependence. And so unfortunately, although it looks like thermodynamics has come in here, it really hasn't, because this has come in as a ratio. So this would slowly come to equilibrium. This would rapidly come to equilibrium, but it would come to the same equilibrium. So there's nothing we can say about the equilibrium constant being 100 that the reaction is fast or slow. And I didn't emphasize that point probably enough as we've gone so far. When we have a equilibrium constant, it says nothing about speed of the reaction. So thermodynamics just says where the reaction is going to end up. It's kinetics that talks about the speed with the rate constants. All right, so that's the connection between some of the equilibrium stuff we've been talking about and some of the kinetic stuff we've been talking about.